Hello everyone, today I will give a report for our paper whose title is Attention Backend for Automatic Speaker Verification with Multiple Enrollment Utterances. This page shows the outline of today's report. First, I will give an introduction and the motivations of our proposed method. Next, I will introduce two different conventional backend models. Then I will introduce our proposed attention backend model in detail, from the model architecture, trials sampling method, as well as the loss functions. Next, I will show the experimental results on two different datasets. Finally, I will conclude this report by the conclusions we obtained from the experiments. First, let's see these figures. It shows the general architecture of a speaker verification system, including the front-end speaker encoder for extracting speaker embeddings, and the back-end model for measuring pairwise similarity. The typical speaker encoders include the time delay neural network and its variant called ICASSP. Recent is another choice for speaker encoder. As for the backend model, cosine similarity is the simplest one, which is utilized to measure the similarity between enrollment and testing utterances. The other is probabilistic linear discriminant analysis, which can alleviate the channel mismatch problem. Inspired by PLDA model, neural PLDA model was proposed to use a neural network to simulate the behavior of a PLDA. Previous study almost focused on single enrollment case. There is little literature shows how to handle multiple enrollments. However, the case of multiple enrollments is more robust in real-world setting, and multiple enrollments contain more acoustic variations of enrolled speaker. There are two common operations for multiple enrollment case. First, concatenating waveforms or acoustic features of the enrollment utterances. The other one is the averaging speaker embeddings of the enrollment utterances. So, can we use multiple enrollments more efficiently in a neural backend? Yes. In this paper, we propose a attention backend model, which utilizes two different attention mechanisms to make better use of multiple enrollments. In our paper, we use the scaled dot self-attention to learn intra-relationships among speaker embeddings of multiple enrollments, and we also use the feed-forward self-attention to aggregate a very number of enrollment speaker embeddings by adaptive weights. Next, I'm going to simply introduce the conventional backend models. Okay, let's say the multiple enrollment case. Suppose an enrolled speaker has k utterances. Not k is a varied number. We can concatenate all utterances, like this figure shows, as a long utterance. Under this operation, the multiple enrollment case is switched to the single enrollment case. Alternatively, we can also extract the speaker embedding for each utterance. Then average this speaker embeddings to get a center vector to represent this enrolled speaker. In this way, the following process is same with the single enrollment case. No matter which method we use, the multiple enrollment case is switched to single enrollment case, and we can use cosine score or PLDA model to measure the similarity between enrollment speaker and testing speaker. However, there is no interaction among enrollment utterances. So, in this report, we propose a novel attention backend model to introduce the interaction among the enrollment utterances. Next, I will describe our attention backend model in detail. First, let's say the model architecture. Similar with previous description, we also extract the speaker embedding for each enrollment utterance. Next, these embeddings are stacked as a matrix denoted as a capital E. Then, the scaled dot self-attention is used to compute the interrelationships among these embeddings. We believe in this way, some latent factor would be emphasized, and some latent factor would be de-emphasized. The output matrix of the scaled dot self-attention will be aggregated by the following feedforward self-attention module and output a vector denoted as H to represent the enrolled speaker. Finally, we compute the cosine similarity between H and the test speaker embedding Q. A logistic regression is used for the score calibration. Next, I will introduce our child's sampling method. In this method, we can introduce multiple enrollment process in training stage, and the interactions among embeddings can update the parameters of neural network by backward propagation. Okay, I'm going to introduce this method step by step. First, we load the speaker balance the mini batch from dataset, which means the number of the embeddings for each speaker in one mini batch are same. For example, in the right table, there are three speakers A. There are three speakers A, B, and C, and each speaker has 4 utterances, whose index range from 1 to 4. Then the data in the mini batch will be rearranged to form testing enrollments trial pairs. For positive pair, testing, embedding, and enrollment data come from same speaker. We select one embedding as a testing embedding, and the rest of this same speaker is used as enrollment data. For negative pair, testing embedding is marked by the check symbol, and the enrollment data is marked by 3 cross symbol of other speakers included in this mini batch. As for the loss function used in our attention bank model, we use a weighted sum of binary cross entropy loss and generalized end-to-end loss. Here there is a hyperparameter used to combine these two loss functions, denoted as a lambda. In our experiment, we set this lambda to 0.6. As for the binary cross entropy loss, by using the sampling method mentioned in the previous page, binary cross entropy loss can be formulated by this formula. By this formula, here L and N indicate the speaker. If testing speaker and the enrollment speaker are same, the indicator this indicator function will return 1, otherwise it will return 0. As for the generalized end-to-end loss, it can maximize the between class distance, meanwhile minimize the within class distance. Next, I will introduce the experimental result of our attention packet model. First, let's say the datasets used in our experiments. In our experiments, we have 2 different experimental settings. The first is for single enrollment case. In this case, we use the vocal syllable as a dataset. It contains more than 7,000 speakers and more than 2,000 hours speech data. All of the utterances come from the YouTube video of celebrities in English. In the other experimental setting, we use the same syllable dataset. It includes more than 1,200 hours speech data, and different from vocal syllable dataset, which only included interview data. Zeng syllable has 11 different genres, including some hard scenarios like scene and entertainment. Please note that the number of the enrollment utterances of the evaluation protocol in Zeng syllable dataset is varied. In our experiments, we use 4 different speaker encoders to extract the speaker embeddings. The first is the time delay neural network with statistical pooling. The next is the resident 34. Both of them are speaker encoders without frame level attention. We also use the speaker encoders with frame level attention. The first is time delay neural network with attentive statistical pooling. The next is the ECASSP DNA. We use this speaker encoders to show that our attention backend, the attention mechanism used in our attention backend is different from the frame level attention in the speaker encoder. Next, let's see the result and analysis. First is the single enrollment case on Vox table. This table shows the result of the single enrollment case. From the table, we can find that our backend model is comparable with the PLDA model in terms of EER, even if there is no interrelationship in enrollment utterance. As for the mean DCF, the proposed model slightly outperformed the PLDA model, which proves that our model works reasonably well for the single enrollment case. Next is the result for multiple enrollment case on Zeng syllable. These two figures shows the performance of ER and mean DCF respectively. For concatenation and mean operation, we give the best performance of causa similarity over PLDA model. And from these two figures, we can know that despite of the criterion, our proposed attention backend realized the best performance in the multiple enrollment case. Finally, let's say the ablation study. This table shows the result of the ablation study. First, let's say the first line. It decomposes our attention backend to 5 parts: scaled out self-attention, feed-forward self-attention, logistic regression, binary cross-entropy, and generalized end-to-end. Next, let's say the second line. It masks the scaled out self-attention out, as the figure shows. Next is the let's say the third line. It substituted the feed-forward self-attention with the mean operation, like this. From the second and the third lines of the table, two self-attention mechanism, we can note two self-attention mechanisms both contributed to the improvement. Next, let's remove the logistic regression. From the first line, we can also say that logistic regression for score calibration was another essential component of the proposed model. Next, let's remove the binary cross-entropy and generalize the one by one. From the comparison of the fifth and sixth slides, we say that the proposed model using binary cross-entropy only had lower ER than using generalized end-to-end loss only. While one using generalized end-to-end loss resulted in a lower mean DCF score. Combining binary cross-entropy and generalized end-to-end, this resulted in the lowest values for all metrics. Finally is the conclusions for our report. In our research, we found that conventional backend models like causa similarity and PLDA model cannot work well in multiple enrollment scenarios. So we proposed the attention backend model, which utilizes two different attention mechanisms to make better use of multiple enrollments. The utterance level attention mechanism can improve the performance further even if the frame level attention mechanism and the spatial mechanism have been applied in speaker encoder. This page shows some reference for our report. Please, if you are interested in it, please have a look. Thanks for listening.